In this video, I want to demonstrate how to conduct a confidence interval for a population proportion and all the different pieces that are attached to it. I should mention that when we're doing a confidence interval for proportion, there's been a fundamental change. We are now working with qualitative data. We're working with categorical or qualitative information, like do you have a tattoo or not? Earlier, we saw a population mean and the confidence interval for it, but we were working with quantitative data there. So we were trying to estimate the average time it takes someone to drive to the university. Quantitative data and qualitative data are fundamentally different, yet when it comes to working with the confidence intervals, we're going to see there's a lot more similarities and differences between them. And so in this video, we're going to talk about confidence intervals for proportions, and proportion will be the proportion in the population that have a certain characteristic. You're going to notice that we're working with a parameter called P, and that's a population proportion. The point estimate, the best guess of that, is our sample proportion, and we call that P hat. We know from one sample to the next that the sample proportion will vary. They're not always going to be the same, so we need to understand how they're going to vary. And to do that, we're going to look at something called the sampling distribution of the sample proportion. And there are several pieces that we need from that. Now, earlier in the semester, the section dealing with sampling distributions actually had a section dealing with the sampling distribution of the sample proportion. I opted not to cover that section, and I told you that we would just look at the results that we need when we get to the confidence intervals, and later on when we get to the test hypothesis information as well. Well, it turns out the sampling distribution of the sample proportion has three unique characteristics, and we need to understand them a little bit. Remember, the sampling distribution is you take a sample, you calculate a statistic, and then you pile them up. Well, the way they're going to pile up, we're going to find out, follows a nice normal distribution. You'll see that in just a second. What we're going to be interested in is where's the center of that sampling distribution. So if I draw the sample proportions piling up in a normal curve, what we find out is that sometimes the sample proportions are lower than the population proportion, sometimes they're larger than the population proportion, but on average, they're exactly equal to that population proportion P. And so you can see I've drawn it here with P in the center. We called that the unbiased property earlier in the semester. The next step is to consider how varied, how spread out these proportions are. And you can see I'm drawing a couple points that are spread all over the place. Well, it turns out the standard deviation of the sampling distribution of the sample proportion is the square root of PQ divided by N. Now, where's that come from? The same people that brought us the sigma over the square root of N earlier this semester. It just is. It's got a different spread than the population, but that's what we're going to use, and that's what the computer's going to use in the calculations. The last step is to consider the shape of the sampling distribution of the sample proportion. And what we know is that there's a version of the central limit theorem that says its shape is approximately normal. And so that's what you're going to see, a normal distribution centered at P, and the standard deviation is PQ over N underneath the square root. And so those are the same three pieces that we've seen before. Exactly the same things we saw with a population mean. Symbols change, but the idea stays exactly the same. Now, one thing that is going to change is our sample size requirement. The sample size requirement for means was 30 or more. For proportions, it's this thing, and this thing is ugly. N times P has got to be greater than or equal to 15, and N times Q has got to be greater than or equal to 15. It looks weird. It is weird, honestly. But a couple things I'll say. First, it's consistently weird. Whenever we're working with proportions, we're going to see this as our sample size requirement. Whenever we're working with means, we're going to see 30 or more. So it will be consistently weird. The second thing I'll mention to you is it's not as bad as it looks. Now, it looks pretty bad, I'll guarantee that. But when I go through an example next and you take a look at this, you're going to see that it's not too terrible of a sample size requirement to actually use in practice. So hold that thought. We'll come back to that. So here's the setup that looks very much like the setup we've seen before for confidence intervals. What comes out of this, if we have a large sample, we get a confidence interval, and I didn't put this formula in your notes. It's P hat plus or minus a z-value, and I'll subscript that with alpha over 2, times the square root of PQ over N. And if you're wondering, why is he writing so slow? I'm writing with a mouse. There we go. And so as you look at this confidence interval, it's completely new, but it looks a lot like what we've seen before. X bar plus or minus Z alpha over 2 times sigma over the square root of N. It's exactly the same kind of confidence interval. We're going to get two numbers from a printout. So we're going to get a lower endpoint and we're going to get an upper endpoint. And as you've heard me say before, that's a terrible number sign right there. As you've heard, you've heard me say that before. As you've heard me say before, I'm not concerned with the calculations so much as I am with the interpretations, which we'll get to in the example in a second. So I want you to see this confidence interval idea as one main idea with several different applications: a large sample mean, a small sample mean, and a population proportion. All right, now before I leave this page, let me make one extra comment. You may hear my dogs in the background. That's not the extra comment, but they're starting to get upset. Hold on a second. I'm going to pause and come back. All right, I think I have calmed the storm. I have a little dog and a big dog, and the big dog wanted to eat the little dog. All right, so with the little dog in my lap, what was I saying? I remember. One more comment I want to make. If you follow what we've done before, you could probably guess what will happen when I move from a large sample to a small sample, right? With a large sample, the central limit theorem wouldn't work. And so the Z distribution in the formula wouldn't work here. And so I'd have to find something to replace that. Well, what do we replace Z's with? T's, of course. And of course, we use T with n-1 degrees of freedom. And then let's say that for the T distribution to work, we need the population of X's to be approximately normal. Now, if you followed that kind of thinking, go from a Z to a T, we need the assumption of an approximately normal population. That's exactly what we've seen before, but it doesn't work now. That's the problem. When you're working with numbers, quantitative data, and you're working with means, those numbers may fall into a normal distribution. But when I'm asking you questions like, do you have a tattoo? Are you going to register for a summer class of Stat 2? You're either answering yes or no. And when you answer yeses and nos, you're never going to get a normal population. You can't get anything that even is close to a normal population. And so the assumption that we need to get to the T distribution will fail whenever you're working with qualitative data. So when you're working with quantitative data, we have large sample confidence intervals, but no small sample confidence intervals. All right, let's take a look at an example. All right, in this example, we're interested in estimating a proportion of all USF students who does have a tattoo, or do have a tattoo. I randomly sample 235 USF students and find 67 of them that have a tattoo. And we want to create a 95% confidence interval for the population proportion. Now, again, some of you guys have had a stat class in the past where you've done a lot of calculations, but that ain't my class. No calculations necessary. So I went to my software, put in the value of the sample size, put in the number of successes, and here is, let's see if I can get it, there we go. Here is the confidence interval that we get. Now, if you want to do the math, you can. I just don't want to do it. So a lower endpoint of 0.227, a higher endpoint of 0.342. Now, before we do any interpretations, we need to make sure we have a large enough sample. And the question I'm going to ask you, it's going to show up on an exam, and it's going to look something very similar like this. And it's going to ask, is this a large enough sample? And you're going to come here and you're going to say, wow, look at that number. Yeah, that's large, because look how much bigger than 30 it is. And I'm going to give you that option on a multiple choice exam, and it's just not right. 30 has nothing to do with proportions. When you're working with proportions, you have to check n times p. Now, what's p? P is a sample proportion. Actually, p isn't the sample proportion. P is the population proportion, but we're not going to know that. We're trying to estimate that. And so what we do in these sample size checks, we're going to use a sample proportion. And so we're going to take the 235 and multiply it by the sample proportion, 0.28511. And you're going to notice that I'm just doing little math tricks. It's going to get me to the 67. Oops, sorry about that. It's going to get me to the 67 people that said, yeah, I have a tattoo. And we have to make sure that that number is at least 15, and of course it is. Well, we also need to check n times q. There's a two-part sample size check. And again, because I don't know q, I'm going to have to use the sample q. Well, what is q? Q is the proportion of failures. So Q hat's going to be the proportion of failures in the sample. It's the opposite. So if this is P hat, my sample proportion of successes. Q hat is going to be, that's a lousy Q. Q hat is 1 minus that. What's 1 minus 0.28511? It's that number there. And when you do the math, when you multiply the 235 times the proportion of a failure, if you want to call it that, you get the number of people that said, no, I don't have a tattoo. And what you're going to see me write in my notes here is, since both of these are at least 15, n is considered large. And so you see me write this criteria as n times p and n times q both have to be greater or equal to 15. But in reality, in practice, it's so much easier than that. I have to sample enough, in students in this case, but I have to sample enough experimental units, more generally, so that I get 15 successes and 15 failures, at least 15 of each. As long as the math works, this is going to be the number of successes, and this is the number of failures. They need to be at least 15. So the actual sampling of this is relatively straightforward. When I'm asking, hey, did you attend a football game last season? I have to sample until I get at least 15 students that said, yes, I did, and 15 students that say, no, I didn't, and then I'll have a large enough sample. If I take a sample, and what gets interesting here is, depending what you're asking, it's kind of easy. With a tattoo, it's not hard to find 15 yeses and 15 nos. But if I start to get more specific, if I start asking things like, do you have a barbed wire on your bicep? A tattoo of barbed wire on your bicep, then all of a sudden it's like, well, gosh, that's a very unique thing I'm asking for. And so it's going to take me a lot longer to get 15 students to say, yes, I do. Does that make sense? And so your overall sample size is going to raise dramatically as you get more and more obscure with the things you're asking, or as the probability of observing that outcome gets smaller and smaller. And so the sample size being large isn't just a value n that you got to worry about it, but it's relative to the proportion that you're working with. So anyway, that's the sample size check. Please note that it's not 30 or more when you're working with proportions. That's the change. This is the really, from my perspective, from my seat, this is the big change when you move from means to proportions, because watch how we're going to do the interpretations. And you can see I've cut down the printout a little bit. Here's our confidence interval. What's the practical interpretation? Well, we think the proportion's in there. Except we do better than that. We think, well, we're 95%. We lead with our confidence, right? We're 95% confident that the proportion of all USF students who have a tattoo falls between those two numbers. It's the same way we interpret any confidence interval. It's the confidence level, it's the parameter, it's the values. Think about how you did your interpretation with means. Wasn't it the same? The parameter changes. We're talking about the proportion of all USF students that have a tattoo. We may have been talking about the mean high price of all NASDAQ stocks before. And then you got some numbers. And the numbers obviously change from one sample to the next. What do you mean when you say you're 95% confident? Well, we mean exactly what we said before. This is one interval. If I sampled again, I'd get a different interval. If I sampled over and over and again, I'd get different intervals. And I know that 95% of them, they wouldn't contain mu, because we're estimating a population proportion here. It's P. And so it's the same exact idea. Now, if you've taken a live class with me, you know that I stand up front with my hands cupped and it looks like an interval, and then I say, what happens when we take a different sample? And it shifts to the left and it shifts to the right. And I refer to them as the dancing intervals. We got dancing intervals around the value of P. It's the same idea. I can't emphasize that enough. And of course, these are the two typical interpretations that you see used with confidence intervals. I'm going to ask you some questions. What do you think? Is P equal to 25%? I read an article years ago that said the population proportion of all students that have a tattoo is 25%. What would you say if this was your interval? Notice the value of 25% falls inside my interval. Maybe. At the 95% confidence level, the proportion of all USS students that have a tattoo might be 25%. It might be 23%. It might be 30%. It might be 33%. Any value that I ask that falls inside those endpoints is a potential value for P. I don't want to say it is 25% because it may not be. It might be. Is P equal to 35% or 0.35? Notice every single value in the interval now is below that value, and so I'm going to make a strong statement and say we are 95% confident that P is less than 35% or 0.35. Is P equal to 20%? Same idea. We are 95% confident P is greater than 20%. Is P equal to 0.23? Notice the 0.23 falls really close to that endpoint, doesn't it? 23%. I'm going to say maybe, man, the 95% confidence level, P might be 23%, but I'm thinking, gosh, I'm really close to that endpoint. It's frustrating. It's killing me. Why? Because if this interval were a little narrower, this is the confidence interval we have now. Let's just draw it like this. Here's the lower endpoint at 0.227. Here's the upper endpoint at 0.342 there. And I'm asking about a value that falls just inside that lower endpoint. If this interval were narrower, if these endpoints pinched in a little bit, can you see how that 23% might pop out on the outside and I'll be able to make a better statement? And so that's where we head to next. Is there some way, do we have some control over how wide or narrow our confidence interval is? And the answer is yeah, we do. And so the next step is to work on determining the sample size. But that's a time for another video, or it's a good place to stop. So I'm going to stop here. And when I come back next, I'll talk about determining the sample size, and we'll take a look at a confidence interval for mu, a confidence interval for P, and some of the things we have to think about, and we'll do some examples. So until then, so long.